Have you ever wondered how a self-driving car can spot a pedestrian? Or, how your phone magically finds all the faces in a photo? Well, it all starts with something really fundamental, teaching a computer how to see. And in this explainer, we're going to pull back the curtain and look at the actual math that lets a machine make sense of the visual world.
So, let's start with a really basic question. When you and I look at a photo of a car, we instantly see its shape, its outline, the edges. It's automatic for us. But how on earth does a computer, which only thinks in numbers, do the same thing?
Okay, let's use this picture as our example for today. It looks like a pretty normal photo, right? But here's the thing. To a computer, this isn't a car. It's not a church, it's not a gravel road, it's just data. A huge organized pile of numbers.
And here's what that data actually looks like. Believe it or not, every single digital image you've ever seen is just a grid of pixels. The best way to picture it is like a giant spreadsheet. And each little cell in that spreadsheet holds a number that represents the color and brightness at that one tiny point.
And that number, it's called pixel intensity. Now, to keep things simple, let's just think about a grayscale image like ours. Every pixel has a value from 0, which is pure black, all the way up to 255, which is pure white. Every single shade of gray you see is just a number somewhere in between. This, right here, is the basic language a computer uses to understand images.
So, okay, we've got a grid of numbers. Big deal. How do we get from that to actually finding the edge of a car? Well, the answer lies in a really powerful mathematical trick called convolution. This is the magic process that translates all that raw pixel data into features that actually mean something.
And the star of the convolution show is this little thing, the kernel. You'll also hear it called a filter. People use the words pretty much interchangeably. A kernel is just a small matrix, a little grid of numbers, and it's specially designed to find one specific pattern, like a vertical line or a horizontal one, or pretty much any kind of edge.
The process itself is actually surprisingly simple when you break it down. First, you take your input image, that big grid of pixels. Then you take your small kernel and you slide it over every single part of the image. The math you do at each spot creates a totally new grid, and we call that a feature map. You can think of it like a new image where the only things that show up brightly are the exact features the kernel was built to find.
All right, let's peek at the math for just one position. And don't worry, it's not that scary. The kernel gets placed over a little chunk of the image. You just multiply each number in the kernel with the pixel value it's sitting on top of. Then you add all those little results together. That final sum, that becomes the value for a single pixel in your new output image. Then the kernel just slides over one spot and you do it all over again for the entire image.
So the main idea here, the intuition, is that convolution is basically a pattern matching game. A kernel that's designed to find vertical edges is going to have a pattern of numbers that represents a sharp change from left to right. So when it slides over a part of the image that has that same pattern, a vertical edge, bam, it produces a really high value. It's literally just searching for and lighting up the parts of the image that look like itself.
Okay, theory is great, but let's see some of these famous kernels in action. We're going to start with two absolute classics used for detecting horizontal and vertical edges, the Prewitt and the Sobel filters.
So here are two different kernels, both designed to find vertical edges. See the pattern? Negative numbers on the left, positive on the right. That setup is perfect for detecting a change from dark to light. But look closer at the Sobel filter. It puts a 2 and a -2 in the center row. That small change gives more weight, more importance, to the pixels right along that central line. And, as we'll see, it can produce a much stronger result.
And here it is. This is the Prewitt filter applied to our car. We basically run both a vertical and a horizontal kernel over the image, and then combine the results. And look at that. The filter has essentially erased all the textures and shading, and it's left behind a really clear outline of the car, the church, and the horizon. Just like that, it has found the edges.
Now, let's see what that little tweak in the Sobel kernel's numbers actually does. This is the output from the Sobel filter. The overall shape is the same, of course, but notice how the lines just seem brighter, more intense. That extra weight we talked about lets it find those edges with a lot more emphasis, giving us a much more defined picture.
So Prewitt and Sobel are great, but they do require two separate passes, one for the horizontal edges and one for the vertical ones. So that begs the question, what if there was a different way? And that brings us to our next one, the Laplacian filter.
The Laplacian filter works in a totally different way. Instead of looking for an edge in just one direction, it's designed to find edges in all directions at the same time. It does this by hunting for points where the pixel brightness changes most sharply. This means it can find vertical, horizontal, and diagonal lines all in a single pass. The one major downside, though, is that it's super sensitive to any noise or grain in an image, which can sometimes make the output look a little messy.
And here's what that looks like. The Laplacian output has a really different feel to it, doesn't it? It highlights all these fine details and areas where things change fast. But you might also notice it's a bit darker overall, and maybe not as, quote, bold as the Sobel filter. It's capturing a whole different kind of information about the image's basic structure.
So we've seen 3 different filters, and they've all produced 3 pretty different results. You know, the best way to really get a feel for the differences is to just see them right next to each other.
This side-by-side really makes the difference between Pruitt and Sobel pop. Take a look at the body of the car and the roofline. The Sobel output there on the right is just consistently brighter, more pronounced. That little bit of extra weight we talked about in the kernel really does make a visible difference in how strong the detected edges are.
Now, let's compare Sobel with the Laplacian. Sobel, on the left, gives us these really strong, thick lines representing the edges. The Laplacian on the right gives us much finer, sharper lines. It almost looks like a pencil sketch. So it's amazing at pinpointing the exact location of an edge, but it just doesn't give you that same sense of intensity that you get from Sobel.
So here's the big takeaway. We started with a normal photograph that, to a computer, was just a meaningless grid of numbers. And by applying a tiny little matrix of numbers we picked out, a kernel, we were able to transform that random data into something structured and meaningful, a map of the object's edges. This simple idea is a fundamental building block for all of computer vision.
And that leaves us with a pretty mind-blowing question. We just use simple, predefined kernels to find basic edges. But what happens when a machine, through deep learning, starts creating its own kernels, thousands of them, far more complex than these? It starts to find not just edges, but textures, patterns, complex shapes, and eventually faces, cars, and cats. The basic process we just saw is the same, but the scale is just incredible. And it really makes you wonder, what else will they learn to see? Thanks for joining us.